Later I started studying math and computer science at the University of Warsaw, and already at the end of my studies, I was working on intelligent transportation systems, so in the transportation domain. So I was developing a software for simulating traffic and algorithms for optimizing road traffic in cities by traffic signal control. And I learned that AI algorithms can be helpful, can be very useful for this task. So I started learning more about AI. And so it was at the end of my graduate studies, my master studies. And the results of my work were quite good. So I was always very interested in doing research. So I decided to apply for PhD studies at the same university, at the University of Warsaw. And that's why I just decided to continue my research and exploration of the AI domain. So it was already about 15 years ago. But then, since I was working in the transportation domain, in particular, I was also interested in autonomous vehicles and self-driving cars. So at some point, I was invited to talk about it in the radio, and there was an interview with me, and one person after the interview contacted me, and it turned out that he's the founder of a startup that was called Bohr Technologies. So Bohr from the last name of Niels Bohr, of course. And he told me that he would like to develop quantum computing algorithms for optimizing transportation, optimizing logistics. So my first impression was, wow, I didn't know that quantum computers are already so advanced that we can try to apply them to optimize logistics. But I got very interested and I started learning about it more. That's why I started working in the quantum computing field, because I learned that indeed there are already, so even though we still do not have, let's say, very powerful quantum computers, but from a theoretical point of view, we already know some algorithms for optimizing transportation and optimizing logistics. And this is how my quantum journey started. And later I also got involved in many other initiatives, and I believe that later during this interview I will have opportunity to tell more about them.
Right, interesting. Well, of course, you were one of the organizers in Warsaw Quantum Computing
Yes.
Club,
Yes.
and of course, you noticed that in any club, in any quantum computing club, you will find them flourish in a diverse environment. So, so many teams. Some can uh, can focus more in programming and others on hardware or theoretical aspects. So, what strategies do you recommend for overcoming the challenges of understanding new topics? How can
Yeah.
they effectively connect theoretical physics to real world
Mhm.
application in technology?
Yes, this is a very good question. So indeed, as you said, at some point I started organizing meetups of the Warsaw Quantum Computing Group that I founded. It was November 2018. And it was a very good decision, because I started building and developing our local quantum computing community. So indeed, even before, we have some good research groups at the universities or Polish Academy of Sciences. But I would say that these communities were not very integrated. So people already knew each other, but for young people, for students, it was not that easy to learn more and got involved and just got connected with some senior researchers. So thanks to organizing these on-site meetups in Warsaw, I gave people an opportunity to meet. First of all, to learn, to listen to interesting lectures given by some invited professionals or researchers. But each of these lectures were also followed by the after party, so something like a networking part, where people had opportunity to meet and discuss, just got connected. So indeed, it significantly contributed to building and developing our local quantum computing community. But coming back to, so that was a good opportunity for people to learn and also to meet people who have different expertise. Yes, because so when I was organizing these meetups, I usually also try to ensure the diversity of the topics. So sometimes I invite a specialist in quantum algorithms. Sometimes there were specialists in quantum hardware, depending on the current needs and availability of the experts, of course. And so coming back to the second part of your question, it's quite tricky indeed. It's because this quantum computing and domain, or even when we look even broader on quantum technologies and not only quantum computing, this area is already very broad. So it's very difficult, or maybe even not possible to be really an expert in all aspects of quantum technologies. So usually it's good to focus on one, two, or three fields. So even if you focus only on quantum algorithms, there are also so many different areas in this domain. So everything depends what is interesting for you and what is your background. And I think that if your background is in computer science or mathematics, I believe that a good way to start getting involved in the quantum domain is by quantum computing and quantum algorithms. So start reading about quantum algorithms, attending some lectures on quantum computing or quantum algorithms. There are already many very good talks, lectures that are recorded and available on the internet, or there are some good tutorials, and there are already some good quantum libraries like Qiskit or Penelane. So it's and there are very good tutorials helping people learn how to use these libraries. So there are already good opportunities. In terms of quantum hardware, I would say that it's more difficult because usually it's good to like have some hands-on experience both with quantum computing or any quantum hardware. In case of quantum computing, you can already try to access some quantum computers or simulators of quantum computers available somewhere in the clouds. But in case of quantum hardware, it's more challenging because let's say, really good quantum hardware can be very expensive and not easily available, especially in some areas. So it's more difficult. So but if someone has background in physics or engineering, maybe it's good to focus on quantum hardware and maybe try to go for studies to some universities or research organizations having good access to this quantum hardware just to learn more. Yeah, so probably this is this could be the best recommendation. So in general, if your background is in math or computer science, it's probably easier to start from this quantum computing and quantum algorithms domain. If your background is in physics or engineering, it's probably easier or better to start from quantum hardware.
The next question, I guess it's one of the most repeated questions of all time. How can students in quantum computing club best prepare themselves for a career in quantum computing? What specific skills and knowledge area they need, they should focus on, especially if they are still in the early stages of their education?
Okay. Yes. So since my background is in math and computer science and not in physics, then it's difficult for me to tell something about this, let's say, more physical and quantum hardware part, but I can tell a lot about quantum algorithms and quantum computing. So in general, there are already some good educational materials available for free on the internet. So in particular, I can surely recommend you educational materials developed by Qword. So the organization that I'm currently leading as the chairperson of the board as well. All our educational material. So in general, in Qword, we collaborate together internationally. We have members from many countries, and we already have many local groups in more than 30 countries. These groups are called the so-called Q cousins, like Q India or Q Turkey, or Q Iran or Q Pakistan, and we can also think about Q Palestine. And people from all these countries collaborate together to prepare these educational materials. All these educational materials are available for free under open source licenses, that is Apache license. And these local Q cousins are also responsible for organizing educational events, the so-called workshops on quantum computing and programming for their local communities based on the educational materials that we develop. And as Q-Word, we also help in organizing these events. So we teach people how to organize these events. From time to time, we even organize workshops for to just train new instructors and new mentors of these educational workshops. These workshops can be on-site, they can be also online, so then people from all over the world can join. So this is a good way to start learning about quantum computing, starting from really the basics like linear algebra or programming in Python. So we have a dedicated preparatory course that is called QPrep. Then the next level is the introduction to quantum computing and quantum programming that is called QBronze. And then we already assume that the participants know the basics of linear algebra, the basics of probability theory, the basics of Python programming. And then there are more advanced intermediate level workshops like Q nickel, Q silver, Q titanium, where people can already learn about some more advanced quantum algorithms like Shor algorithm, quantum Fourier transform, Grover search algorithm, Deutsch-Jozsa algorithm, Simon algorithm, Bernstein-Vezirani algorithm, and so on. There are dedicated materials and workshops on quantum annealing or quantum key distribution. So we already have several different types of educational materials that people from all over the world can access, and they can learn on their own, but they can also join the workshops that we organize from time to time for free.
Well, you already had answered multiple of our questions, but there is one question. How can students actually select this material based on their current level of expertise and team focus?
Yes, so as I mentioned, in Q-Word, we've developed several types of education materials at the different levels. So I think that and for each educational material, we have a brief description of the content and of the requirements, so everyone may assess what is her or his current level in order to just select the proper workshop and the proper educational material. And we also have our Discord community server, where we already have a few hundred or maybe already a few thousand people, and there are some dedicated channels where people can ask questions. So if someone is not sure which workshop should select as the next, they can also ask the question, and some people from Q-Word may try to help and answer. Yeah, so this is what I can tell about these workshops and educational materials prepared by Q-Word. But as I said, we know that there are many other educational materials available on the internet, but for some other educational materials, it's really hard to say. And everyone should maybe just briefly review the description or some first modules of the given course, if a given material, to see if the level is appropriate. And in the worst case, it's good to just start from the very beginning and maybe just repeat even some basic concepts. So the repetition is always good in the education. I cannot hear you now. You are muted.
Your mic.
I was talking there's so many resources available right now, so
Yes.
people or students should prioritize. You think it's best to prioritize our learning based on our interest or skills we have, or what exactly?
Yeah, I think that as I answered during the previous question, from my perspective, so everything depends, right? So, but anyway, the interest of a given person is the most important, the interest and the current level. And I believe that if someone has more background and interest in math and computer science, it's better to focus on quantum algorithms. And there is a lot of open questions in the quantum algorithms domain. If someone has more background in physics and engineering, maybe it's better to focus on quantum hardware. But I also know many physicists trying to just move to the domain of quantum computing and quantum algorithms. If someone doesn't have background in programming, it's also good to maybe take some courses, introductory courses to programming, especially in Python or Julia. So Julia is the second most important programming language for quantum computing. And maybe also some courses on algorithms and data structure or complexity theory to learn more about complexity classes, estimating, or at least to be able to understand computational complexity, time complexity, memory complexity of different algorithms. So these are just the basics that usually computer science students just learn during their studies. But for people with background in physics, these concepts might be new. So it might be good to just learn first the basics of computer science. And the other way around, if someone has background in math or computer science, but not in physics, it's good to read some good good books or good courses, take some courses on the basics of quantum mechanics in general. And as quantum mechanics, the theory of quantum mechanics is already quite old, there are already many good resources. Like I remember that there is a very good book written by Susskind, so Essentials of Quantum Mechanics, or there's a similar title. So I can later maybe recommend something. But yeah, I can maybe later post some links here on the chat because on the website of the Quantum AI Foundation, which is a non-profit organization that I'm leading, we also have a sub-page dedicated to resources, and there are many links with links to some good educational materials as well.
Yeah, I've attached the link for Keyworld on the chat, so everyone can go and check it out. But I don't know if you have this question, Amani, on your list, or if I can ask it early on. But I think it's an important one to really ask it before we run out of time. It's about like recent projects that you worked on, a research project in quantum computing that really interests you, and you feel like you see that it has a future, and people should, or students should, pay attention to that research or that certain paper.
Okay, good. So maybe just to conclude the previous part, I just shared a link to the website with some links to good resources, good learning resources. Okay, but regarding your question about my projects, so since 2019, I've been working on quantum algorithms, quantum, but also classical and machine learning algorithms for optimizing logistics. So in logistics, in transportation, there are many combinatorial optimization problems that are NP-hard, like traveling salesman problem or vehicle routing problem with some constraints, like with limited capacities of the vehicles or time windows. So these are just the kind of problems that I've been working on. And together with my research group, we've been trying to tackle these problems from different perspectives and from different sides and using different quantum approaches, starting from quantum annealing. Later, we also explored variation quantum algorithms like variation quantum eigensolver or QAOA and variants of these algorithms. We've also explored some hybrid algorithms combining classical part with some quantum solvers. We've also applied some machine learning techniques to enhance or to improve some quantum algorithms as well. So we've already tried to tackle these optimization problems from different perspectives. But if you ask me if it's, let's say, really promising area, I cannot say it for sure because it's good to know that in this, let's say, logistic optimization, transportation optimization domain, there are already many good, well investigated and established classical algorithms, and it might be very, very difficult for quantum computing to give any advantage in this domain, and probably not in the nearest future. So I do not expect that it will be one of the first areas in which quantum computers will bring an advantage. But I can tell you about another interesting project That was proposed by my colleague from Poland, Dr. Jarek Duda, and I can also share you a link to the website with some good resources, because a few months ago he proposed an idea to build a two-way quantum computer, in which the state preparation is implemented on both sides of a quantum circuit. And so this is a very interesting idea, inspired a bit by hydrodynamics, actually, and it's not difficult to prove that if we are able to build such a two-way quantum computer, then we should be able to solve NP-hard, NP-complete problems in polynomial time, which is probably not true for classical one-way quantum computers. So these two-way quantum computers, in some aspects, could be more powerful than classical one-way quantum computers. But of course, currently, the open question is whether we will be able to build such two-way quantum computers, because it hasn't been done yet, and there are some, let's say, engineering obstacles, and maybe even obstacles from a theoretical physics perspective as well. But if you ask me about some very interesting, promising ideas that can bring a significant breakthrough, I would say that this is something that can bring a real breakthrough in the quantum computing domain.
Well, talking about projects, in your opinion, what are the most promising applications in quantum computing and artificial intelligence?
Yeah, so it's still hard to say, because the problem is similar to the problem of optimizing logistics, because we already have so good machine learning algorithms, and the domain of classical machine learning is growing so fast that it can be really difficult and challenging for quantum computers to bring us an advantage, especially taking into account that classical devices like GPUs from NVIDIA or TPUs or some other processors that are currently under development in many companies are already very, very powerful. So in general, if we want to, let's say, just run classical machine learning algorithms faster, it might be difficult. But there are some ideas to, let's say, build some hybrid architectures, quantum classical architectures of neural networks, for example. Or there are some kernel methods based on quantums, SVMs, quantum support vector machines. So then the advantage may not come from, let's say, having better or greater computational power, because I don't think that it will be possible in the nearest future. But there are just totally different architectures. And I have read some research papers claiming that in some areas, especially quantum support vector machines or quantum neural networks, have provided some advantage over classical methods. But in none of these papers, it was proven that this, let's say, hybrid quantum classical architectures are really the best possible, and there will now be some other classical algorithms that are better. So I'm pretty sure that there can be, for all these tasks and for all these research papers, there probably exists some other classical machine learning algorithms that can give better results. So as for now, I would say that it's really hard to say, and to be honest, I rather expect that the more promising are the applications in another direction. So applications of classical machine learning to improve quantum computing. So from my perspective, this can be even more promising, at least in the nearest future. But in the long term, once we get to the level when we have really powerful quantum computers, I believe that this hybrid quantum classical neural networks can probably give some advantage, at least in some applications, but this is just my guess.
One last question. What are the most significant challenges currently hindering the widespread adoption of quantum technologies, and how can the next generation of researchers contribute to overcome these challenges?
Okay, so from my perspective, from my experience, The main problem is the quantum hardware. So first of all, the quantum hardware is not powerful enough. So the contemporary quantum computers are still relatively small and still very noisy. So because of the noise, we also need to apply some quantum error corrections methods. So the number of physical qubits that we have is not the same as the actual number of logical qubits that that can really operate as the quantum theory predicts. So this is the biggest challenge, and as you probably know, there are many approaches to build quantum computers, from superconducting to ion traps, photonics, or neutral atoms. But it's really hard to say which of these approaches will turn out to be best, and some researchers even claim that we even haven't discovered the methodology, the approach to build quantum computers that will be, let's say, the best possible, or the best in 50 or 100 years from now. So it's really hard to say. And the other problem with quantum hardware is the availability of the existing quantum computers. So even these still very noisy and relatively small quantum computers are not easily available. So even in the cloud, like IBM's cloud or D-Wave or Rigetti, it's not that easy to get access, because the number of quantum computers available quantum computers is still relatively small. The demand is high, so usually the researchers have to wait for a long time in the queues to just get access to the actual quantum hardware. So so the quality and availability of the quantum hardware is the biggest obstacle now. Another obstacle is probably from the quantum algorithm side, because actually there are still not that many quantum algorithms for which we can really prove, or at least expect, that they will really give quantum advantage over the best possible classical algorithms. So there are maybe about 10 typical quantum algorithms, and there are also many variants of them. And there's still a huge field for improvements, in my opinion, and a lot of research need to be done in the quantum algorithms domain as well.
Thank you for your time and answers. That's all for me. If you want to talk, Sarah.
Thank you so much, Amani. Thank you so much, Professor Gora. We noticed that there's an intersection, I believe, in your journey, in our journey, because we're still trying to improve the local community of quantum computing. So that is inspiring, actually, for me, and I believe for the students here. Thanks also to the internet that we can do such stuff and we can learn without having to be, offline and together. So we really appreciate the world we're living in right now. Thank you again. And I don't know if anyone has any question. We are running out of time. It's 4:30, but if anyone has a quick question, please ask it. Okay. I think we asked the right questions, and I think everything was answered perfectly and precisely. So thank you for your time, and thank you everybody for your time as well.
Thanks for having me. I wish you good luck and all the best in your quantum journey. So
thank you. I appreciate it.
Thank you.
Goodbye.
Bye bye. Goodbye.
Bye. اوكي يا جماعة يعطيكم العافية. ما بعرف إذا حدا بده بده يسأل إشي، عنده اقتراح. أماني شكرا، يعطيك العافية على وضع الأسئلة أنت وفريقك. وبنشوفكم في لقاء يوم الثلاثاء. طبعا يمكن 20 حدا اعتذر منا اليوم، بس it's okay، رح يكون اللقاء مسجل.
قدينا احنا اوريدي اللي حضروا.
ثواني.